Our universe is a vast and mysterious place, filled with wonders and enigmas that boggle the mind. We can see stars, planets, and galaxies with our telescopes, revealing the beauty and complexity of the cosmos. But there is something else out there, something we can't see with our eyes or even our most powerful instruments. It's called dark matter. Dark matter is a mysterious substance that makes up about 85% of the matter in the universe. Despite its abundance, it remains one of the greatest mysteries in modern astrophysics. It doesn't interact with light, which means we can't see it directly. This elusive nature makes it incredibly difficult to study. But we know it's there because of its gravitational effects on visible matter. These effects can be observed in the way galaxies rotate and how light bends around massive objects. Imagine a bowling ball on a trampoline. This simple analogy helps us understand the complex nature of gravity. The bowling ball represents a galaxy, and the trampoline represents space-time. The weight of the bowling ball creates a dip in the trampoline. The bowling ball creates a dip in the trampoline, just like a galaxy creates a gravitational well in space-time. This well affects the motion of nearby objects. Now imagine that there are a bunch of invisible bowling balls on the trampoline too. These represent the dark matter. These invisible bowling balls would also create dips in the trampoline, even though we can't see them. Their presence is inferred by the way they influence the visible matter around them. This is similar to how dark matter affects the universe. It shapes the structure of galaxies and clusters, guiding the formation and evolution of cosmic structures. We can't see dark matter directly. It's invisible to our eyes and even to the most powerful telescopes. So how do we know it's there? How can we be certain of something we can't see? Astronomers have observed several phenomena that can only be explained by the presence of dark matter. These phenomena include the bending of light around massive objects, known as gravitational lensing. One of the most compelling pieces of evidence for dark matter comes from the rotation of galaxies. When we look at how stars move within galaxies, we notice something strange. Stars and galaxies orbit the galactic center much like planets orbit a star. But unlike planets, the star's speeds don't decrease as expected with distance from the center. However, the speed of stars in the outer regions of galaxies is much faster than expected based on the visible matter alone. This anomaly has puzzled scientists for decades. This discrepancy suggests that there must be some invisible matter providing the extra gravity to hold these fast-moving stars in their orbits. Without this unseen mass, the stars would simply fly away. This invisible matter is dark matter. It doesn't emit, absorb, or reflect light, making it completely undetectable by conventional means. Its gravitational influence is crucial to understanding the dynamics of galaxies. Without dark matter, our current models of the universe would fall apart, unable to explain the observed behaviors of galaxies and galaxy clusters.
Dark matter plays a crucial role in the formation and structure of galaxies. In the early universe, dark matter's gravity caused ordinary matter to clump together. These clumps of matter eventually grew large enough to form stars and galaxies. Without dark matter, galaxies would likely not have formed at all. They would not have had enough gravity to pull in the necessary matter. Dark matter also forms a halo around galaxies. This halo acts as a scaffolding, providing the gravitational support needed for galaxies to hold their shape. It influences the distribution of stars and gas within galaxies.
Scientists are trying to figure out what dark matter is made of. It's a big challenge. Many experiments are underway to try and detect dark matter particles directly. One approach is to build extremely sensitive detectors buried deep underground. These detectors are shielded from cosmic rays and other sources of background noise. They are designed to look for the faint interactions that might occur if dark matter particles collide with ordinary matter.
Another approach is to try and create dark matter particles in the lab. Particle accelerators, like the Large Hadron Collider, smash particles together at extremely high energies. Scientists hope that these collisions might produce new particles, including dark matter particles.
Section 5. The Bullet Cluster, a cosmic crash and dark matter's fingerprint. The Bullet Cluster is one of the most compelling pieces of evidence for the existence of dark matter. It's a pair of colliding galaxy clusters approximately 3.7 billion light-years away from Earth. When these clusters collided, the hot gas within them interacted and slowed down. However, the galaxies themselves and the dark matter associated with them passed through each other relatively unscathed. This resulted in a separation of the visible matter, the hot gas, and the dark matter. By observing the gravitational lensing effects of the bullet cluster, astronomers were able to map the distribution of both visible and dark matter. Section 6. Beyond the Standard Model, New Physics on the Horizon. The Standard Model of particle physics is a highly successful theory that describes the fundamental particles and forces that make up our universe. However, it doesn't include a particle that could explain dark matter. This suggests that there must be new physics beyond the Standard Model waiting to be discovered. One leading candidate for dark matter is a hypothetical particle called a weakly interacting massive particle, or WIMP. WIMPs are thought to be heavy, slow-moving particles that interact very weakly with ordinary matter. This makes them extremely difficult to detect directly.
Section 7. Cosmic Microwave Background, Echoes of the Early Universe. The cosmic microwave background, or CMB, is a faint afterglow of the Big Bang. It provides us with a snapshot of the universe as it was just 380,000 years after the Big Bang. The CMB contains tiny temperature fluctuations that reflect the distribution of matter in the early universe. By studying these fluctuations, cosmologists have been able to determine the relative amounts of ordinary matter, and dark energy in the universe. The CMB observations provide strong evidence for the existence of dark matter and its important role in the evolution of the universe.
Section 8. The mystery deepens, surprising discoveries and anomalies. While the evidence for dark matter is compelling, there are still many unanswered questions.
Recent observations have revealed some surprising discoveries and anomalies that challenge our current understanding of dark matter. For example, some dwarf galaxies appear to have less dark matter than expected. This has led to speculation that dark matter might behave differently in these environments.
Additionally, some observations have suggested that dark matter might interact with itself in ways that we don't yet understand. These findings could have profound implications for our understanding of the nature of dark matter. Section 9. Alternative theories modifying gravity's grip. While dark matter is the leading explanation for the observed gravitational anomalies in the universe, some alternative theories have been proposed.
One such theory is modified Newtonian dynamics, or MUND. MUND suggests that Newton's laws of gravity might need to be modified at very large distances or in very low gravity environments. This modification could potentially explain the observed rotation curves of galaxies without the need for dark matter.
However, MOND faces challenges in explaining other observations, such as the bullet cluster and the cosmic microwave background. While it remains an intriguing alternative, MOND is not as widely accepted as the dark matter hypothesis. Section 10. The future of the mystery unraveling the dark matter enigma. The search for dark matter is one of the most exciting and challenging frontiers in modern physics and astronomy.
Future experiments and observations promise to shed more light on this elusive substance. New generations of dark matter detectors are being built with increased sensitivity. These detectors will be able to probe a wider range of dark matter particle candidates.
They will search for even fainter interactions. Space telescopes, such as the James Webb Space Telescope, will provide us with even more detailed observations of distant galaxies and galaxy clusters.
These observations will help us to map the distribution of dark matter with greater precision. Section 11. Conclusion. A universe yet to be fully known. Dark matter remains one of the greatest mysteries of our universe. Despite decades of research and countless observations, we still know very little about this elusive substance. It's a testament to the vastness of our ignorance and the endless capacity of the cosmos to surprise us. Every discovery we make seems to open up even more questions. While we have learned much about the gravitational effects of dark matter, its true nature continues to elude us. We know it exists because of the way it influences galaxies and clusters of galaxies. The quest to understand dark matter is a journey into the unknown. It's a challenge that pushes the boundaries of our scientific knowledge and technological capabilities. It's a search for new particles, new forces, and potentially new dimensions. Scientists are using advanced particle accelerators and detectors to try and catch a glimpse of dark matter particles, and perhaps even a deeper understanding of the fundamental laws of physics. Theoretical physicists are constantly developing new models and hypotheses to explain dark matter. As we continue to explore the cosmos and probe the depths of matter, we can be certain that more surprises await us. Each new mission and experiment brings us closer to unraveling the secrets of the universe. The universe is full of wonders yet to be revealed. From the smallest particles to the largest structures, the cosmos holds countless mysteries waiting to be discovered.